Hello everyone, let's see this particular question. So here we have proof based question where we are supposed to prove the left hand side is equals to right hand side. Now if we will take the left hand side, so this is our left hand side. Here you, as you can see, sigma, that means summation of all NCR minus 1 to the power r, and then we are having I. This I, yes, this is imaginary unit, imaginary number, iota I we are having over here, which you have seen in complex numbers. So I to the power r plus I to the power twice r plus I to the power thrice r plus I to the power 4r. So yeah, as we know that I is nothing but root minus 1, which is written over here as well. And if we will try simplifying it more, we know that I is square value is minus 1. Okay, so from here we can simplify this I to the power twice r, and we can write it as I to the power twice r can be written as I is square and then power r by using law of exponent. Now this I is square is nothing but minus 1, and we are having minus 1 to the power r. So at the place of I to the power 2r, we can write minus 1 to the power r. Is that making sense? Similarly, here we are having I to the power 3r as well as I to the power 4r. So can we write this I to the power 3r as I cube and then power r? Now as we know, I cube value is minus I, and if you don't know, please find it. Minus I to the power r. This is what we are getting. Similarly, I to the power 4r we are having, which can be written as I to the power 4 and then power r. And as we know, I to the power 4 is nothing but positive 1. So we will substitute here and we'll write this is nothing but positive 1 to the power r. Now let's substitute these all in our expression. So we are going to get summation r 0 to n NCR minus 1 to the power r. I to the power r we will keep as it is. I to the power 2r can be written as minus 1. Let me highlight it. I to the power 3r we have also calculated. This one. Yes, we can replace it with minus I to the power r. And I to the power 4r can be written as 1 to the power r. So this is what we are having. Now we will simplify it more, and we are going to, let's multiply this NCR with each and every term. Okay, let's keep the summation sign as it is, and let's take this NCR and open the bracket like this. Then the next term like this. I hope this much is clear to you. Let's continue. So this is our last step. Let's apply rule of exponent over here. Can you see this minus 1 to the power r, okay, and I to the power r can be written together. So we can write it as NCR, and this 2 by using law of exponent can be written in terms of multiplication together. So we can write it as a minus 1 times I, and both are having power r like this. Making sense? Similarly, let's apply rule of exponent for all the other terms. So minus 1 to the power r multiplied with minus 1 to the power r in the next term can be written as minus 1 into minus 1 and having power r, right? Like this. Same goes for the next term. So we are having minus 1 into I, which can be directly written as minus I, right? Same goes for the next term. Here in a smaller bracket, we are having minus 1 into minus 1, which can be directly written as just 1 to the power r, right? Same goes for the next term. We are having minus 1 into minus I, which can be written as just I to the power r. And same for the last term, which is minus 1 into 1 can be written as minus 1 to the power r. Let's write it. Now let's distribute this summation sign with each and every term. So the first term will have r summation r is equals to 0 to n NCR minus I to the power r. Similarly, the next term will have its own summation, that is r is equals to 0 to n NCR 1 to the power r. and same goes for the remaining term. Now as we know the formula for binomial expansion, that means if we are having a plus b to the power n, this can be written as summation of r is equals to 0 to n ncr a to the power n minus r b to the power r. Right? We can also write it in this form, and yeah, we can expand it as well. So as we know, our format somehow looks like the formula only, but our a is missing. So let's take a as a 1. In each and every part, let's take a as 1. Okay, I mean that here in the first part, let's write ncr minus 1 to the power r is there, fine, but in between let's drop that. Our a can be written as a 1 to the power n minus r. I am highlighting this green color part. Can you see that? I am talking about the middle one where I have introduced this 1 so that I can use the binomial formula. Is that making sense to you? Similarly, for the next term, see carefully, everything is arranged already, but the a is missing somehow, so we can take the a as a 1 to the power n minus r. Getting it? Same goes for the next term. So yeah, this is what we are having in our hand. Let's simplify it further. Now let's use the binomial formula, and the first term can be written as, by using the formula, that 1 minus I to the power n. Making sense? Similarly, the next term can be written as, here the a is also 1 and b is also 1, so we can write it as a 1 plus 1 to the power n. Okay, the next part, here a is 1 but b is just I, so it can be written as 1 plus I to the power n. And the last term, a is 1 and b is minus 1, so that can be written as 1 minus 1 to the power n. Now the first term, that is 1 minus I to the power n, let's keep it as it is. The next term, that is 1 plus 1, can be directly written as a 2 to the power n, right? Similarly, the next term, that is 1 plus I to the power n, we'll keep it as it is, and 1 minus 1 is nothing but 0, so 0 to the power n is just 0, so we will exclude that term. Now just look at the right hand side's expression which we are supposed to prove, and there we are having 2 to the power n, which we have also got, but apart from that we are having 2 to the power n by 2 plus 1 cos n pi by 4. So cos is involved, so this is indicating that we have to represent our complex number in polar form, then only we will be getting cos theta, sin theta, maybe sin will get vanished. Okay, so let's represent this complex number 1 minus I and 1 plus I in polar form. So 1 minus I can be written as we know, if z is a complex number, that is 1 minus I, z can be written as r cos theta plus I sin theta, where r is the modulus, that means under root, a square, that means 1 square, plus b square, that means minus 1 square. Okay, this is our r, and cos theta plus I sin theta, we need to find theta, that means argument of this complex number. As we can see, this complex number 1 comma minus 1 is lying in the 4th quadrant, right? And in 4th quadrant, if we are having the complex number, theta is nothing but minus alpha, right? And alpha can be found by using this formula which is written over here. Okay, so alpha is nothing but tan inverse b by a. Okay, mod of b by a. So tan inverse, our b is minus 1 by 1, which is nothing but just pi by 4. Theta is equals to minus alpha in the 4th quadrant. So we'll be taking minus pi by 4. So we are getting cos of minus pi by 4 plus I sin minus pi by 4. Okay, which is nothing but root 2. Cos of minus theta is just cos theta, so we'll write it as it is, cos pi by 4 minus I sin pi by 4, as sine of minus theta is minus sin theta. Got it? So this is, we are having the polar form of the given complex number. Similarly, we will write 1 plus I as well. Now 1 plus I again r cos theta plus I sin theta As we can see, 1 plus I, this is lying in the first quadrant. Okay, so here we are having r again will come out as a root 2 cos pi by 4 plus I sin pi by 4. Let's substitute it. So we have got 1 minus I as root 2 cos pi by 4 minus I sin pi by 4. But here 1 minus I to the power n is there, so root 2 will take its exponent n, and this one will also take its exponent n. Okay, plus 2 to the power n we will keep as it is, and 1 plus I we got as root 2 cos pi by 4 plus I sin pi by 4. Again here exponent n is there. Okay, this exponent n, what to do with that? So we will distribute the exponent. Root 2 will take its exponent and this expression will also take its exponent. Now as we know, de Moivre's theorem in complex number says that if z is a complex number in polar form, that is r cos theta plus I sin theta, then z to the power n can be written as r to the power n in bracket cos n theta plus I sin n theta, right? So similarly in our case we were having z as a 1 minus I to the power n, which we have converted and written as, and we have also given this exponent to root 2. Now de Moivre's theorem says that this can be written as cos n pi by 4 minus I sin n pi by 4. Is that making sense? And yeah, this root 2 to the power n will remain as it is, right? Let's use it. So we can write in our expression root 2 to the power n as it is, and cos n pi by 4 minus I sin n pi by 4 by using de Moivre's theorem, plus 2 to the power n, I am copy pasting as it is, plus root 2 to the power n, okay, cos n pi by 4 plus I sin n pi by 4. Now let's take root 2 to the power n common and let's see what are we getting. So if we will take root 2 to the power n common, we are getting cos n pi by 4 minus I sin n pi by 4 plus, I am taking the last part as well. From here I have taken root 2 to the power n common. So we are getting cos n pi by 4 plus sin I sin n pi by 4 plus 2 to the power n will remain as it is. Now here we can clearly see I sin n pi by 4. Okay, one is negative, another is positive, it will cancel out each other, and we are going to have root 2 to the power n. Okay, 2 times we are having cos n pi by 4 plus cos n pi by 4, which is nothing but 2 times cos n pi by 4. And yes, this 2 to the power n is still there. Now we are almost done. We just have to take this root 2 to the power n and 2 together. So this root 2 to the power n is nothing but 2 to the power n, and root means power 1 by 2. So from there it is coming as a n by 2, right? And again one more 2 is there. So this exponent will get added over here. Cos n pi by 4 plus 2 to the power n. So yes, we got left hand side is equals to right hand side. Is it clear to you? If you are having any confusion, please comment in the comment box. Thank you.